Okay, so it's a great pleasure to have Marcelle Soares-Santos here. I want to make a lengthy introduction because you'll see I get very emotional with this. I think we are, as we were discussing the coffee break, we're really lucky that we are alive at this moment in history. So for my personal life, it's the most single exciting discovery I've seen because of many reasons. And I think that's the first detection of gravitational waves, and then the first multi-messenger are like two events that will be, marked in the history of humankind. So not like in our personal lives. And it's even a greater pleasure to be having Marcelle delivering this talk. I've been known her for a long time and seen her career, so it's nice. You can look at the CVs and so on, so I won't make this lengthy introduction, but she's been one of the lead persons to look for the optical counterparts of gravitational waves. That was like maybe a very, like a shot in the dark, very ambitious, but at the same time with not assurance of having a result. So that was very courageous move, I think. And she was really one of the persons involved in getting, the Dark Energy Survey, which is one of the largest wide field surveys in operation, in convincing people that it's worth looking for an optical counterpart, setting up all what is necessary technically to get into this. And well, the results you hear now. Thanks.
Thank you. So thank you very much for this beautiful introduction, and also for the invitation to come here and talk to you about this work. And I'm really proud, and I really love to talk about this, so I can talk about it forever. So I hope somebody will keep the time score. And what I'm going to focus on is the idea or the emergence of multi-messenger astronomy, and what are the consequences and the opportunities that exist for some of you here as young scientists, young physicists, to explore this new window into the universe. In particular, I'm going to focus a lot on the idea of using these newly discovered events for cosmology, which is that's closest to my heart. But as I'm going to show, there are opportunities here for pretty much everyone. I mean, there is a broad range of topics that can be covered, and that's one of the reasons why this result is so exciting. So to begin, let me just say that so I am currently an assistant professor at Brandeis University in Boston, and I'm also a member of the Dark Energy Survey collaboration, which also has a strong participation of Brazilian collaborators, including some of them here at this institute. So I'm very proud to be a member of this collaboration, and you will see, I'll talk a little bit more about what that is all about, and what it was our role in the discovery of the optical counterpart of the first neutron star merger event detected ever. In order to set the stage for the talk, I'd like to introduce and to start with this image, which shows up in the paper that I led with these results. And this image is not only for your enjoyment, it also contains useful information, and I'll guide you through it. So what you're seeing here is a galaxy that is in principle not very remarkable. It's an elliptical galaxy like many millions of others that we detect with our camera. It's not very remarkable. And you can see here that there is a source in this galaxy that was present on August 17 of last year. And 14 days later, that source is gone. So with this, you already can have an idea of two of the challenges associated with discovering the optical counterpart of a gravitational wave event. This little dot here corresponds to the location of the source of the gravitational wave event GW+0817. Unfortunately, we are not very creative in naming these objects. So that it's stands for gravitational waves and the date when the event happened, okay? And so GW170817 was this merger of two neutron stars, and I'm going to tell you all about it, but this is the location where it happened. And the source, as you can see, it is bright enough that, for example, you can easily see it in this image even with your naked eye. You wouldn't even need a sophisticated computer software to find it in this case. But it is gone only 2 weeks later. So it's a very ephemeral, transient event in the sky, okay? And about the brightness, of course, that this is an event, if you know a little bit more about this galaxy is it's relatively close. So in absolute terms, this luminosity it's relatively bright, but it's not that great. So it tells us that it's not going to be super easy to find these objects, and that's the reason why we had not seen one until now. Now, why is this event in particular so important? What is special about this? I like to say this because oftentimes when I give a talk about this subject, people remember that the Nobel Prize was awarded just last year for the discovery of a merger of two black hole events, which was the first ever detection of gravitational waves. So I often get the question, didn't they already collect the Nobel Prize for this? Why should I pay attention? So for me, GW170817 is even more important than the event that resulted in the Nobel Prize award, because it was the first event that had a counterpart in the electromagnetic spectrum that we could observe. That means that we could combine all of the wealth of methods and ways that we have to observe and study astrophysical objects with this new way of studying them, that's with gravitational waves, to obtain new combined information. Everybody in the community was waiting for this moment, for a merger that would have not only black hole events, but a merger that would have at least one neutron star. Could be a black hole and a neutron star. In this case, was two neutron stars. And we are very excited that only 2 years after the first detection, we were able to actually see one of these. So I said that there are many opportunities for scientific endeavors to be explored with these data sets. And here I'm going to, this list is not a complete list by any means. It's just a list some of the topics that you could study by combining gravitational wave and electromagnetic signatures from the same events. So if you are by any chance interested in astrophysics and you want to learn about the origin of the heavy elements in the universe, there is something for you there. We believe that those mergers are the major mechanism by which those elements are formed, and the details of it will be available to you. If you are instead interested in the origin of binary systems in the universe, there again we are going to get a population of those systems. Or if you're interested in cosmology, as I am, then we can use those events for cosmological measurements as well. I'm going to tell about how we can do that. And if you're interested in fundamental physics, such as new tests of general relativity in extreme environments, or a very traditional particle physics type of event of just comparing the time of arrival of these two different messengers, we can do that. And if our neutrino colleagues are able to detect them as well, we may or may not be able to have a race of three particles, which would be extremely exciting and fun. We're not there yet, but so what am I, a little bit of an outline of the talk. The first part I'm going to continue to wrap up on the motivation for why we are doing this and describe the current program that we are doing and where we are going, how it's working. And on part two, I will talk a little bit about the future prospects, which I think are really exciting, and in particular, I think for the audience, it might be of interest. So let me talk about the motivation for cosmology. In this case, what you're looking at here is a plot that I borrowed from a paper by Rees et al., one of the key groups pursuing measurements of the rate of expansion of the universe using supernova. And what you see here is the rate of expansion of the universe. Different dots here represent different observables that were used. I would say pay attention only to this one, which is the latest and greatest measurement coming from supernova. These results were published in 2016. And compare these results with the latest and greatest results from the Planck satellite. Two things that I think stand out from this plot. First is the size of the error bars. We know the rate of expansion of the universe with an uncertainty of 2.5% with supernova, and with an uncertainty of 1% from the cosmic microwave background. If this doesn't make you feel excited about this, you're probably in the wrong career, seriously. We're talking about knowing that in a box of 70 megaparsec on the side, if you look at this box again 1 second later, it has grown by about 1 or 2 kilometers. Right? This, I think, it's a spectacular achievement of our community in terms of observational astronomy. Now, what is the second thing that you notice if you look, ignore all the other dots there, just think about this one and this one. What's the other thing that you notice? They are not in agreement with each other. This discrepancy here is of about 3 sigma, which is not something that in particle physics probably you wouldn't write home about it. But it is tantalizing. And in particular, I don't have this plot here, but if you see the history of these measurements in time, you see that the more precise they get, the more diverging they seem to get. So what could be causing this discrepancy? One possibility would be systematic uncertainties not accounted for, systematic effects not accounted for in either of the measurements. And in this case here, keep in mind that this plot was made by the supernova people, so they think, oh, if they are wrong in the CMB community, this is how much their results would move to agree with ours, right? So this probably would be the other way around if it would be a plot made by the CMB people. So keep that in mind. But here, this arrow is showing by how much you would have to change the lambda CDM cosmological model in order to make the CMB results agree with supernova. So if both teams are right, if there's no systematic effect unaccounted for in either side, this could be a smoking gun of new physics, including perhaps smoking gun of the existence of a new neutrino species. So if you make N effective be 3 but 4, you are going to get you're going to get a result that would be compatible between these two. So wouldn't it be great if we could disentangle these and figure out if those two results are correct? So the community is pursuing this. There are groups investing a lot of time, energy, and resources in both sides of this. And there are groups as well investing in other observables to do that. And right now, what we think is that gravitational waves may provide an additional method that is totally independent from these two, that will allow us to put a dot here with an error bar of about 1%.
The size of the halo there is how much is going to change?
Yeah. So if you, exactly. So one example is this. This is curvature, right? So if you decrease the curvature from 0 to minus 0.001, this dot would move to here. If you make N effective be the current best value of N effective, which is 3 point a little bit, and add +1 to it, you would add it, put it here. That's the idea. But this is done only to illustrate by how much this effect would go. So when I see this plot, I see an opportunity to design a program to go after this, and with the idea of the possibility of detecting gravitational wave events, we may have an opportunity for real to do this in an independent method, in an independent way. So how so? How can gravitational waves help us? To do this, I don't expect you guys to read this, don't worry. I'm just saying that the idea is not new. The idea that you could use gravitational wave events, from mergers of compact objects as standard sirens for measurements of the Hubble constant. This is not new. This is, was first proposed in the 80s. And the idea, and by the way, this paper is really cool. It's 3 pages only, maybe 4 or 5 equations only. When I grow up, I want to be able to write papers like this. So here's the idea, and this is again from that same paper. So the idea is that the change in frequency, we know that what is happening with is a quadrupole system that will emit gravitational waves. So you have a binary system rotating like this, and as gravitational waves are emitted, the orbits decay, and they will get to a point where they will be spinning. They will be rotating at a significant fraction of the speed of light and merge. So the rate at which this orbit decays, so the change of frequency, df, dt, is going to depend on the mass of the 2 components in the system. The more massive, the faster the decay. So, once you know the mass of the system, the amplitude of the wave, the intrinsic amplitude at the position of the source, is also depending on the mass in the same way. So if you measure this, you measure the waveform, you measure how quickly the frequency is changing when you approach the merger time, you know what's the intrinsic amplitude. Now I go in my detector and I look at what is the apparent or the observed amplitude, and I do the ratio of the two, I know how far the waves are. How far the source of the waves are. So it's a very simple way, and it doesn't depend on any details of the astrophysics of the system, unlike supernova that depend on a number of possible sources of systematics. So if we do that, we could imagine making a Hubble diagram similar to this one. This one was made with supernova, which I call these days the traditional methods. So in this case, we would get distance to the events from this method that I just described. And if we were able to identify the source, pinpoint it the same way as we did on that image in the first slide, if we are able to do that, we can get the redshift, either of the source itself or of the galaxy where the source lives, and we can put a point, make a diagram like this. And from there, we are going to measure the expansion rate of the universe in a similar way that our colleagues did that with supernova, and learned that instead of being a straight line on this plot, the actual curve corresponding to expansion of the universe, it deviates from a straight line, meaning that the expansion is not constant, but it's speeding up, which means that we must have energy to promote the accelerated expansion of the universe. We can do exactly the same thing, minus all of the systematic headache. So, great. So, from my point of view, thinking of this possibility, again, this idea was around for a long time, but finally, we got to a point in 2014 when we were about to have detectors going online that would allow us to make this a reality. Now, when we start thinking about the actual experiment of doing this, we have to face a few challenges. The first challenge is the challenge of the search areas. That image was easy to pinpoint the source. I show you one galaxy. This is where it's happening. I show you the before and after image, and I point with the crisscross where it's located. In the real world, that is not what happens. We are going to have, because of the way gravitational waves are detected, which is in some way analogous to the way sound is detected, you cannot really pinpoint the location with gravitational waves alone. So it's similar to sound. You have your brain is able to process the sound entering your ears and detect that, for example, the sound came more or less from this direction as opposed to this direction, but you cannot really pinpoint anything until you turn your head and look. Here, it's a very similar idea. With two LIGO detectors, H and L stand for the two LIGO detectors, this is the area in the sky as a function of the the confidence that the object is inside that area. So to achieve 90% confidence level, you need something like 500 square degrees. For the non-astronomer in the room, 500 square degrees is a lot. I will show, I'll show, you have an idea soon. To give you an idea, the largest field of view cameras that we are able to construct have approximately, so the largest that exists right now have 3 square degree field of view. So it is not, it's not trivial to cover all that area. And the largest that we are building that will come online in the next few years has about 3 times that, so 9 square degrees field of view. So this is not trivial. And the number of galaxies that you have in that area is a lot. When you add a third detector, and V here stands for Virgo, and as we know, the network of gravitational wave detectors right now is constituted of 2 LIGO detectors in the United States and Virgo in Europe. Then you see that the areas now are smaller by a factor of 10. To achieve 90% confidence level, I need to cover only 60 square degrees. So with a camera with a field of view of 3 square degrees, it's not that bad, right? So not that hard. So with that motivation, back in 2000, so I need to make a pause here to tell a little bit of the story of how this happened, or how did we end up doing this, right? So obviously, so the dark energy survey is a survey that uses this large camera with 3 square degree field of view and the size of a minivan, installed on a telescope with 4-meter diameter in Chile. The idea, when it was constructed, it had nothing to do with this. It was to map out 300 million galaxies and 4,000 supernova to do cosmology using the traditional cosmological probes. We are well in the way of doing it. We've been operating for 4.5 years. It's great. It's spectacular. Now, in 2014, the LIGO and Virgo collaboration sent an announcement to the entire astronomical community, including us, saying, hey, astronomers, we are going to turn on our detectors in 2015, and we are going to be sensitive enough to begin seeing something. If there is, so if there are mergers out there at a distance of out to about 80 megaparsec, we are going to detect them. Would you like to partner up with us to look for the optical or electromagnetic counterparts in whatever wavelength of your preference? I saw this email and my first reaction was to laugh at it and say like, oh no, this is not going to happen anytime soon. These guys are crazy. They're not even commissioning the instrument yet. It's not going to happen. I close my laptop, get my coffee, go to work, and have a long commute. By the time I get to work, I realized that, you know, these guys wouldn't be inviting the entire astronomical community, sending an email to the whole world to watch them fail, right? There must be something. So I went back to my email trash and read that message again and said, oh, I should do what? Oh, okay, so I should sign up here. So I sign up. And, but of course, as a member of a large collaboration, the Dark Energy Survey collaboration has about 300 people. I cannot go there and sign up, oh yes, we are going to do this. I have to convince some of my esteemed colleagues that this is a good idea. Some of them did not think it was a good idea. It's just like, oh, seriously? Or aren't we busy enough? We have a lot of things to do. Luckily, quite a few of them actually were crazy enough to think that it was an okay idea. And so we started doing that. So we did a campaign in 2015. So the beginning, so this announcement was 2014. So we had about a year to prepare. 2015, when the big black hole event merger was detected, we were one of the teams that did the exercise of looking for the optical counterpart. We didn't find anything. These were two black holes. We didn't really expect to see anything. But it was a great exercise. We saw everything that went wrong, and we tried to fix and improve. So we were ready when season 2 started. So season 2 started in December or so of 2016, and went through mid-2017 until August. So the day it was supposed to, the detectors were supposed to be completely shut down, I think it was something like August 20. And we were seeing a rate of about 1 event per month-ish, right? So, no, even less, 1 event every other month about, right? So we collected a few events and so on, all of them black hole events, so nothing spectacular. And I was at the time moving institutions from Fermilab to Brandeis. So I decided to schedule the truck to show up and pick up my stuff on August 17. Seriously, I'm not kidding. I mean, but yeah, so that morning at this time, 12:41 UTC, which is about 7:41 a.m. Chicago time, the truck shows up, and I think it's the movers arriving very early, but it's not. My phone is ringing. It's not the truck arriving. It is an alert about this event. So what was special about GW170817? The alert was clearly identified as a merger of neutron stars as opposed to a merger of black holes. So you jump out of bed right there. And second, the distance to the event measured through that method that I described, analyzing the waveform and etc., was 40 megaparsecs. For the non-astronomers in the room, that distance is here. Right? I mean, it's really close. If this would be, to give an idea, a supernova, a typical supernova at peak brightness at this distance would saturate our camera on a typical 90-second exposure, which is the typical length of our exposure times. So it was really exciting. So at this point, what we expect to see, so just to give an idea of why, a little bit of the physics that's going on. So these are 2 neutron stars. They are far enough apart, and they're rotating against, they're just rotating in a binary system. At some point when they get close enough, tidal forces will start to deform the material. And when it gets close enough to the merger, you actually have a fraction of material being ejected from the site. And that is the source of the electromagnetic emission. And that's why, for example, for black holes, we are not going to see events like that, as bright or anything. So this is the mechanism that we, let's say, we had already hypothesized that these sources would be bright enough for us to see based on this picture, right, or based on a model for the emission. And we had a camera that was ready to go to observe, and we had prepared and exercised this several times. So we spring into action. But so does a number of other groups. Because as I said, when, it's something very typical. When you have a good idea, typically many other people have that same good idea. So this list here is not a list of individuals, but a list of teams that were involved in observing this event. Because it was really so close, this event was bright enough that even people with a very small telescope could see it. And so people were extremely excited. And also the idea would be as well that that scenario that I showed earlier, the cartoon description of the merger, because the magnetic field in the region of the neutron stars is so strong, we expect to have particles accelerated to relativistic speeds. So there is a chance as well that you would see gamma rays, X-rays, radio emission, everything in the entire range of the electromagnetic spectrum. So that means that the entire astronomical community, and not only the traditional optical astronomers, were engaged. And that's why we have a list of people, or a list of collaborations, of which DES is, of course, my favorite. So this was, for me, was the largest. I understand that if anyone here is part of the LHC collaborations, 1,000 people on a paper doesn't seem so impressive. You probably have done this several times. But for me, it was the largest endeavor that I ever participated on. And it was very exciting and spectacular in many ways. And different, I think, from what happens to experiments on the LHC, because there everybody's in one collaboration, and here it was not. It was much more complex, right? A complex structure of different collaborations. Okay, so without further ado, let me tell a little bit of the story of GW170817 as a multi-messenger object. So what you're seeing here in the middle, this is a frequency, and this is time. 0 here is the time of the merger, right? And so what you're seeing is what I described earlier. There is a change in frequency. The frequency is increasing as a function of time. And this rate of increase here is what is going to give you the masses of the systems. And the amplitude is, in this case, indicated by the color scheme, right? So so this would be much brighter if it would be a stronger event. So you know what's the intrinsic amplitude, and you can divide that by this observed amplitude, and you would get the distance. Now, what you're seeing on the other two pink plots here is the gamma ray signal from Fermi and integral. Totally independently from the gravitational wave detection, Fermi's satellite saw 2 seconds after the merger time a peak. And normally, I'm not a gamma ray astronomer, but what my gamma ray astronomer friends say is that we see this all the time. We wouldn't have paid attention to it if it was not for the fact that it was in coincidence within 2 seconds from a gravitational wave event. And the integral team also later they looked into their data and they found the same. So when we talk about the beginning of multi-messenger astronomy, there are a few things that we have to be careful about. First is that the beginning of multi-messenger astronomy was decades ago when we first detected neutrinos from the sun and from 1987A, right? So that kind of happened. But the problem is that we took a long, long time to be able to see neutrinos further out than 1987A, which is basically inside our own galaxy. It's not even here. You know, it's really like in your nose. And it's really hard, and it's a challenging thing to do. This is challenging too, but we made a leap of, and I will show how far we can see these events in the future. We made a leap that was otherwise not possible. So. Okay, so this was the beginning of multi-messenger astronomy with gravitational waves. The first time that you have EM and GW from the source being detected. And if this would be the whole story, that would already have been spectacular. And we would be celebrating, we'll be happy already. Maybe I would not be because I work in the optical wavelength, but these guys would be certainly jumping up and down. But there's more, right? So this map here shows the area where things are localized. As I said before, with only the LIGO detectors, the localization area shown here in green is large. It's a lot of sky to cover. If you add Virgo, it becomes smaller. And this bubble here is the region that was Fermi not very localizing the sources either. So this would be it's consistent, but it's not much smaller. So the best localization comes here. This is a zoom in on that region, that banana-shaped region. And shown here are the 50 or so brightest galaxies in that volume, in that area. Because this event was so close, there are not so many galaxies to look at. And this is the reason why people, for example, these authors here, they had a small telescope with a small field of view, so they couldn't cover the entire area. So these squares are the images that they took looking specifically at those 50 galaxies. So it's also interesting, depending on the instrument you have, you use a different strategy, right? So we, in contrast, have a wide field of view camera. So this is that same elliptical, same region. 90% contour is the outermost white contours. So with our camera, we can cover this area rather quickly. So we did actually map out the entire area regardless if there is a galaxy there or not, okay? And another important thing is that we had about 10 hours from the alert time to sunset time in Chile. So we couldn't really start observing right away. We had to wait for sunset. But once the sun set, we had only about an hour and a half to observe before this region of the sky would no longer be observable because of where it was located. So we had to act quickly. But we did cover the entire area multiple times, and it was absolutely great. Now, because this event was very close, we knew that if the source would be of reasonable brightness, it would be visible on the images by eye. You know, we wouldn't need to wait for the automated image processing software that we have that takes another hour, 2 hours to process the images. We wouldn't have to wait for that. We could just look at the images and we would see it. So we had a team eyeballing the images too. That was the eyeball team. So, and that strategy, that mixed strategy really paid off. We found the source. It was one of the most spectacular things that I had the opportunity to experience. And this was one of the members of the eyeball team sending a message to everybody. And this is, again, what he was looking at. And it was great. So what's the protocol when that happens? The protocol is you type in as fast as you can an email and send it to the network of several partners, that list of many collaborations, informing that you found a candidate. At this point, it's a candidate. And it's located on this or that galaxy, and it has a magnitude blah, and that it's worthwhile to pursue. So we are typing this as fast as we can. Clearly, we should have had that template email before, but seriously, we did not have it. And when we are about to send, to press send, we receive another email from the SWOPE team. They found it too. And they found it first. I mean, they beat us by 10 minutes. And the SWOPE team is that team with the small telescope that pointed only at the galaxies. So it happened to be on galaxy number 10 or 11 on their list. And as you can see that their image is a little bit poorer than ours, but it was sufficient for discovery. So I like to show this other than the fact that to give credit where it's due. It's also because oftentimes we think that a discovery like this can only happen if you have the biggest, most fancy instrumentation. Sometimes it's not. And sometimes there is room in an emerging field for more modest instrumentation if it's used in a clever way to make an impact. And I think that's a lesson perhaps that we all should learn. Now, in addition to our two teams, there were 4 other teams. As I said, everybody was looking at this. If everybody who had a binocular at that night was looking at this thing. And so there were 4 other teams that independently discovered this source. And all of them were credited with as co-discoverers of GW17 or 0817's optical counterpart. And that was fantastic, other than the fact that just like, okay, we discovered we can say this gravitational wave blip here came from that particular source in the sky. We also enabled, because it was done so quickly, we were able to get spectrum, we were able to get to see if there was X-ray, gamma ray, radio, etc. It was really a big party in terms of observational data from this one source, everything we could study. Now, but before we go there, as I said, until this point, that little blob there was a candidate. How do we go from a candidate to a confirmed source? And also, another question is, what if it were further away? We were really lucky to get this event so close. What if it were further away? So I will start by answering the first question, and then I'll go to the further away thing. So how do we know that this source is this source and not just something else that happened to be on the sky? So there are different ways of doing this. This is the way that we, in our collaboration, did this. We did the following. We had discovered the counterpart, but we had all of these images covering the entire area. And that was something that no other team that was participating in that big endeavor had available to them. So what we did was we analyzed with our automated software all of the images, and we found out that there were in total, so there are too much detail here, you don't have to just look at the numbers. We had in total 1,500 things, 1,500 little dots that were not there before in this entire region. We apply cuts requiring, for example, that the same thing was detected twice. That means it was not a moving object. That there was not an artifact of image subtraction. And then finally, we require that this was not consistent with a supernova or any other known transient, which means at the end, there was only one source left, and that was the same source that we had identified by eye, which happens right here in relation to the sky map that was provided by LIGO. So this builds confidence that not only we were able to find a source, but we found the right source, right, that corresponds to the gravitational wave event. And it also served as an exercise for us to say, how far could we see this event? Because now we can simulate events and put them at further distance. And the answer is we could have seen this event as far as the limit that LIGO can see today, and the limit, and as far as the limit that LIGO will be able to see once it's upgraded to its maximum sensitivity. So from that point of view, it's good news. It looks like if there are more events like this in the next few years, we are in good shape to detect them. Question.
How well did you know how fast it needed to fade? That was your string is cut, right? It goes from 81 to 1 event. Because we haven't seen one of these before. So
because
how you were on this?
No, so this cut was to reject all the other known transients that typically the other known transients don't decay. If they go from 0, so if from peak to decaying and disappearing here, they don't decay that quickly. So it's the opposite. It's reject. So for example, a supernova, typical supernova, has a lifetime of many weeks.
How sure are we that the neutron stars will not decay very slowly as well? I mean, it's the first time we see one of these, right?
Yes, yes. Okay, so that's a very good question. So the idea is that we have models. So it's the first time we see them, but the model, so this is a model-dependent cut. So the models are that a small fraction of the total mass of the combined neutron star system is ejected. And then you can say, if all that energy is converted into light via nucleosynthesis process, you're going to have a big ball of fire in the sky, and that is expanding. And with that amount of material and that expanding rate, which you calculate by knowing what was the rate there of the merger, you can say that this will cool down at a certain rate, and it will become, the flux will go down by this much. So that's the general idea. Plus, it goes as well as the opacity of the materials, etc. But those are details. In the big picture, you were thinking about the ball of fire. The brightness at the beginning has to do with the amount of energy you had available, the amount of mass that was disrupted from the neutron star. And how quickly it decays is how quickly this shell of hot material expands and cools. So, but yes, it's a model-dependent thing. If you would be, for example, if this model would not be correct, then we would be in trouble. But as it turns out, this model seems to be, at least in general terms, correct. So what's the next thing you do once you say, okay, this is the source, I found it and I identified it? Now you study the hell out of it, right? So you want to understand in detail as much as you can about this source, compare it with your models, and see if it works. So what you're looking at here for the non-astronomers in the room is, you can imagine this as brightness as a function of time in days. 0 is the day, the time of the trigger. Each point here is an observation, and this is a compilation that includes all of our data plus data from a number of people in the community. Everybody made this data publicly available immediately, so it was possible for us to make this plot. And from blue to red here, you're going to redder and redder wavelengths, all the way to infrared bands. And what you can see here is that the overall pattern is brightening within less than 24 hours, then a decay time that is relatively fast. This is 10 days, this is 2 weeks. Our observation that you're looking at was in GRI band, and 2 weeks later, it was barely detectable. So in that image you look, you don't see anything there by eye. In other wavelengths, it was still a little bit there. It turns out that in detail, there's more into this than only this particular simplified model that I described, but the big picture of it was in place. And there's been a number of papers with interpretation and analysis, and this list is not complete by any means, but it provides, I think, an interesting interpretation for the scenario, and it looks like the theories that we had before, at least broadly, they were consistent with these observations. And in the future, we want to see more events to see things in a little bit more detail. For example, we think that there are more than one components with different speed, different velocities of expansion, and that could be the difference between blue decay time. You see that in blue, the decay time is much faster than in red. So as I said, the event was special for people working in different wavelengths. So the plot that I showed before included from, let's say, the UV to the infrared, but now what I'm showing here is what the source looked like in the X-ray. In the X-ray, the emission was delayed by more than a week. So our X-ray colleagues were afraid they were going to be left out of the party, but it turned out that there was X-ray emission, and that is good because it's consistent with the existence of, in addition to this component that I described, which is just the material being heated up and forming this ball of fire in the sky, it's consistent with also having accelerated material forming a jet, and us looking at this jet from an off-axis angle. And then there were observations in radio, and those guys, they really were the last ones to arrive at the party. It took more than 2 weeks for the radio emission to start. So this is 10 days after merger, but they also were the last ones to leave the party, and more than 100 days, this is 200 days after the merger, that source was still visible in the radio. And this is consistent with the idea of the jet achieving the interstellar medium, and shocks and a lot of interesting stuff happening at that scale, which is a little bit later. So this is a really exciting as well for our colleagues in radio astronomy. So let me put the picture here together to build an astrophysical model for what is going on after the merger. So on this side of the picture, what you see after the merger is you're looking at the relativistic outflows. So these are the components that are being accelerated, and where magnetic fields are causing an acceleration in a beam jet like this, which if it would be pointed directly at us for this event, being so close, probably this source would have been visible with the naked eye. But it was not. It was with an angle of more than probably 45 or 50 degrees away. And so, but it was still visible. Not visible, detectable in gamma ray, X-ray, and radio. In addition to that, there is this subrelativistic outflow, where we believe that there are two components. One that is more towards the pole of the system, and another one that's more in the equator. And that has to do with difference. So you will have a preferential direction for the ejected material to go through, which is in the plane of the system. when you can imagine the material being slingshotted away from the system, and there will be a preferential direction where things will be denser. That means a higher opacity, and so it is harder for photons to escape, so you're going to have redder material here. It's also denser, heavier material, and so it's going to be very hot, but expanding slower. And on the poles, you have less material, and then you have a material that is being ejected faster, so it becomes transparent quicker, and then the blue photons escape. This component, what we saw a combination of these two components at the end. We cannot separate them in those light curves, of course. And these components, they generate the light curves in the UV, optical, and infrared that I showed before. Okay, and that's the big picture. Okay, so now we understood what's the astrophysics of the system. What's the next thing you do? You try to look at the, or at least for me, is to look at the environment, right? Look at what's going on there. This is the picture. I showed earlier the image of the galaxy, and I said it's an unremarkable normal galaxy, right? That is true until you start looking in detail. If you subtract the smooth component of the galaxy, you see that there are excess rings here that look like this galaxy suffered a minor merger recently in its history. And in this case, I'm talking about a merger with another galaxy. And there are many scenarios for the formation and evolution of these binary systems that involve disturbances in the galaxy that will get a system that let's imagine a system like the Holz and Taylor pulsar that is very far away and would decay in millions of years, hundreds of millions of years. If that system gets disrupted by something like that in the environment, it could decay to a closer orbit and collapse faster. We don't know if it's true or not. This is just one example, one galaxy, so don't take too many conclusions from it. But I think it's exciting that we can start studying the environment where these things happen. So if we see more happening in this type of environment, it might be interesting. So finally, let me go back to cosmology. I said before that we were interested in, so this is the signal as it looks like in the 3 gravitational wave detectors. These are the light curves, same as shown before, but only with our data, only the data points we collected. Now we were interested in combining these 2 pieces of information to get a measurement of cosmology. What you see here is the rate of expansion of the universe. The CMB and supernova results that I showed before are represented in this plot as these vertical lines here. The y-axis is the inclination angle. I omitted this piece of information before, but there is a degeneracy between the inclination angle and the amplitude of the source. I can talk about that more if you guys want to know about it. And this banana-shaped region here is our measurement with only GW+17 of the rate of expansion of the universe using the gravitational wave events as a standard siren. Now, we cannot distinguish between these 2 scenarios here yet. Our error bars are too big, right? But it's amazing that we already have a measurement. This error bar is about 15%. It has to be a factor of 5 smaller. But if you do the square root of n in your head, you see that we don't really need to have that many events to get there. So that leads me to talking a little bit about the future. So I will skip this one, and I will talk about what we plan to do. So this is the idea. What we want to do is the blue contours here are results for various cosmological parameters as measured by DES. These are the best measurements that we did today. What we want to do is to add the gravitational wave information that shrinks. This is the Hubble parameter, the rate of expansion of the universe. It shrinks this in this direction, and it will hopefully get to a point where it will also allow us to shrink as well our measurements of the W parameter, the equation of state of dark energy. We're not there yet. We are working on it. But this is how much we expect to do in 1 year from now, assuming that the rate of events is as it is. And I'll talk, and this is showing projection for a little bit further in the future. So this is the following. Today we have, so up here is number of events. This is time. We have one event detected. And if we assume that the rate of events continues and the sensitivity of LIGO continues to be as projected, we expect to have in the next 5 years or so, tens of events, up to 100 maybe if the rates. And so the uncertainty, the yellow bar, that the uncertainty on the intrinsic astrophysical rates of these mergers in the universe that we don't know very well. So I stopped this plot here because I think that 5 years is a good skill. I don't know, on a lifetime of a graduate student. it's appropriate time scale of a fellowship or something. And with about this number of events, if I just do square root of n, so I'm not assuming that we are going to make any improvements with respect to what we did before in the analysis side, which is not true. You know that we get better and better as we go. If we just do square root of n, we expect to cross this line here, which is 2% uncertainty on H naught within that 5-year time scale. And that means that in this time frame, which is not very far in the future, we are possibly going to be able to say something about the discrepancy between H naught and CMB.
How do you get the rate of events from one event?
The rate of events we get from one event in the following way. We know, so let me build it backwards, right? So what you can say is rate of event will be number of events per unit volume per unit time. You know that in season 1 and season 2, the effective volume the LIGO was sensitive to was this big, and the effective time that we waited for the first event to happen was about a year. So you use that to, that's one way of doing it. There are other ways of doing this, which is using, you know, what's the rate of, observed rate of binary neutron star events that are not merging, but you know what they are and in our local volume, and we know how long they will, in average, take to coalesce. You could use that strategy as well, which would be more astrophysical. And these arrow bars here, they're huge because of that, because once we have more events, you can just shrink the arrow bars. But for now, that's true. But these arrow bars are consistent with the astrophysical scenario as well. So that's what we have.
1 sigma arrow bar, 2 sigma arrow bar.
These are 90% error bars, yeah. Plus minus 90%. So, yeah, so I think this is super exciting and fun. So I'm getting close to end now. As I said earlier, GW17 0817 was a spectacular event. I think that it was really amazing to be able to be part of this discovery, even if in a small way, right? But to be a part of it. It is, I think, let's say, the impact of GW17 0817 is coming not only from it was the first event of its kind, but from the fact that the community responded super quickly to find a counterpart and study it and get our act together to do this. And that I think bodes well for the future. We are expecting to see many more events, as I showed earlier, and I think that this will be great. So this is all I had to say about this topic. But I have something that's a bonus track for you guys. I hear that there are quite a few people who are interested in neutrinos at this school, and you may or may not have heard that a big neutrino detector located in the South Pole announced a big discovery that also comes with a multi-messenger in the title. So I guess some of you are curious about what's the relationship between one and the other. So in our collaboration, we are actually also pursuing, in a similar way, using the same tools, same techniques, and a lot of overlap between the two teams. We are also pursuing follow-up observations, trying to find the optical counterparts of neutrino events. the motivation for that, so this is a cartoon description of the IceCube lab in the South Pole. I think you are going to hear more about that later, so stay tuned for the next talk in the afternoon and so. And the idea is that there are some models that predict that supernova, regular type 2 supernova, might be able to accelerate to generate neutrinos that IceCube could see. And these supernova, they are, seriously, we throw them away by the dozens every day. So we are really good at detecting them. So we said, okay, it's easy for us when there is an event from the IceCube side that is of interest, it's easy for us to point our camera in that region and localize it. And IceCube, for these type of events, is much better at localizing the region than LIGO. So from that point of view, it's much easier. With one image, we cover the entire area. We go there a second time, third time, just to double check. And quickly, we can say if there is something or not, okay? So we've been doing this for a few years already, maybe a couple of years. And obviously, when the big identification of the event associated with the blazar, that was the result that was just announced, I'm really not going to talk much about this because I know you guys are going to hear about it more. We were one of the teams that also took data on that source as well, trying to see if there was something special there to be found or so. Nothing really. We just see, well, we see the source that was known to be there, and we don't really, in this case, we don't really, unfortunately, we really don't add much information to what we already know from both the gamma ray side and from the neutrino side. But it's quite exciting that we are pursuing this, and we will continue to pursue with this camera other events in the future that are triggered by IceCube in a similar way. So that race of 3 particles, maybe it's on, right? Maybe. Okay, thank you. That's all I have.
Thank you. So I hope you all agree that these measurements was the greatest one until we discovered dark matter. And we do have time for a couple of some questions. So.
Hi. I don't remember if you talked about it, but there is any way to look for good candidates before the events?
No, you mean to see the precursor of, no. So the, let me show, no, this is not going to work this way. But if you remember that image on the title slide, right, where I showed, I didn't show really before and after, I showed during the event and after, right? But if you look at the image before the event, let's say if you took an image 24 hours before or a month before, it looked exactly like after 14 days later. Those, a system with at that distance, 2 neutron stars are not detectable like that, you know, so there's no way we can see them.
Questions?
I have 2 questions, in fact. The first one is, what do you get after the collision? I see the dot, the bright dot, vanish. And what you get, are you expecting a black hole, or what you get after the collision?
Remnant?
Yes, the remnant.
That's a great question.
And the second question is the gravitationals. They can contribute to energy density of the universe, like when you measure the dark energy and dark matter.
So to answer the second question first, in the current universe, they are not going to make a significant contribution to the total energy density. That's not the case. and so they're not going to contribute. They're expected to leave an imprint in the spectrum of cosmic microwave background in the polarization spectrum, and that's a very, very difficult signal to measure. So early on, they were, let's say, the fluctuations were enough to produce this signal, but even then, it's something that is very difficult to measure, right? And the other question was about the remnant. So how do we know? So there are a few ways that you could try to know if what was the remnant. One of them would be analyzing the waveform in the very short period of time right after the collision. And at that point, you could analyze and see if it will be a black hole at the end, you will have the black hole ring down phase, and that would generate a very characteristic waveform. And for example, for the very first big black hole event that was detected, that ring down was detectable. In this case, that ring down phase, if it happened, it was out of band for the LIGO detectors. So from the gravitational wave data alone, you cannot tell because that piece of information is missing. However, from the X-ray and the radio data, the characteristic emission from the jet, etc., it seems to indicate that there is a black hole there in the center as opposed to a neutron star. But it's a little bit of it's model dependent, more indirect than, it would be nice to know that from the gravitational wave data alone, but in this case it was not possible because it was out of band.
Questions? So this goes beyond this 5-year time frame. So in a 15-year time frame, there will be maybe LISA, right, doing gravitational waves from space in a different frequency range. Can you talk a little bit about what kind of follow-ups are already being thought about in this case? Because a different frequency range, and they're going to see much farther away. So it's much more complicated to see, but they're not neutron stars that they're going to see. So.
Yes, so that's a very good question as well. So LISA will be sensitive to mergers of black holes of much larger scale, right? So supermassive black holes. And what people are thinking about, and the other thing is also that LISA, because it's not an L-shape detector to be a triangle shape, so you get the triangulation even with one detector alone, and you are going to be able to get more cycles of the waveform, so you get a more detailed and more localized event. So the localization areas for LISA will be of the order of arc minutes and not degrees, right? And so there are several ideas going on. One of them is for, so these mergers then, so these supermassive black holes, they are in galaxies. So you're talking about galaxy follow-up events and for AGNs and so on. So there are efforts in that direction and efforts of doing spectroscopic follow-up in a way that you would do the analysis. So you're going to see so many of those events that you can do cross-correlation analysis. Even if you don't identify the individual source of each event, you can cross-correlate a large sample with a large sample of galaxies and get better sensitivity, not only to H0, but to the other cosmological parameters as well. So I think that there will be a number of opportunities to do that, and people are starting to think about it, but the focus right now has been more into taking the most out of the events that we are seeing on stellar mass scale.
On the beginning, you talked about the black hole events and you couldn't see it, but there is a way to see the coalescence of black holes, like a ring or something like this?
That's a very, very good question too. So unless if you invoke some exotic physics outside of the standard model and so on, two black holes colliding in vacuum, there will be no EM emission for you to observe. That's unfortunate, but that's the case. However, we know that the astrophysical environments, they are, well, there's matter there. There's it's not a complete vacuum. So there were ideas of people thinking of, okay, in what way you could imagine, for example, if these are stellar mass black holes with an accretion disk of regular matter, and if these accretion disks survive long enough so that they get accelerated, don't get completely disrupted when it's too early, then yes, you could have a jet type of emission similar to what we see from from a single black hole sometimes when there is accretion, right? So that would be maybe, it's not forbidden to happen, but when we do, and I'm not expert in this type of calculation, but when the experts go there and put in general relativity and the physics and try to simulate an event like that, what happens is that the disk, because the neutron stars, they survive until that point when they are very close because they are really the hardest material ever, right? They're nuclear material basically exposed. And for a regular disk made of regular matter that's not degenerate like that, they just get disrupted and fly away before you can actually accelerate anything into a beam or anything like that. So you would need, so there are people with very clever models, but they are all very contrived. So I think, in particular, how can I say, if we have the resources, the observational resources, I would like to continue to follow up a number of these events, say 10 or so in detail, choose the best ones and follow them up, so that we could say, oh, observationally we know that down to this luminosity there is nothing. But probably it will be hard to get the resources to do that because the physical motivation is weak. So, I don't know, maybe if somebody has a more clever idea that can be create a physically motivated model, we can convince people to award some of the telescope time for doing it.
Questions? So why are you okay.
So how the gravitational wave experiments knew it was a binary neutron star system event and not a black hole event?
That's also a very good one. So how do we identify and distinguish between neutron star, or black hole, or even a mixed system? So in the case of a black hole event, the sources, so there's no matter, so what you have are basically point sources until you get to the point where the two event horizons merge, right? So that will have a characteristic wave form. If you take two neutron stars of the same mass and make them go through the same process, the distortion of the mass of the neutron stars, when it gets very close, it will generate small wiggles as well in the wave form. And they will be very distinct, maybe not by eye, but by the software that's used to process the images, the waveforms. And they will be very distinct, and then you can say, these wiggles here, that means that there is mass there. It's not only a black hole. And then at that stage, you know that you cannot tell if it's two neutron stars or a neutron star and a black hole, but you can tell that there is a neutron star because you can tell that there are extra wiggles in the waveform.
Next question. So there's only one guy we didn't talk about, which is the black hole neutron star merger, right? So when we have a pair, because you said the binary neutron stars, which produce the kilonova, the binary black holes, which produce nothing, and then you have the neutron star black holes, which should produce something. So my question is, the kilonova is something was even predicted before. Now, a neutron star black hole, what's the difference in order to do a follow-up? What kind of signal do you expect, and which, is it only optical, also gamma rays?
We expect something very similar from the neutron star black hole merger. Because, so the only difference is that, so it's also a kilonova, but the differences have to do with how much material you will have available. So, and again, we haven't seen one yet, so all we have right now are models. So we think that the amount of material you will have available to become bright will be less because you have only one neutron star instead of two. But at the same time, the shape of the potential well of the system where this material is falling and so on is such that you could have a denser material, a denser shell of material that would maybe ignite it would expand at a faster rate. So then depending on the model you put in, you would have brighter or a little bit fainter and decaying a little bit faster or slower, but not by an order of magnitude, it's by factors of a few. So within the range that we could observe still if everything is okay. So currently, we think that we will use the same strategy. If a mixed event would be detected today, we would use the same strategy and try to, for the search and discovery phase, we would use the same strategy as we used before, and then from there we adapt it once we know a little bit more.
Next question.
What other kinds of astronomical objects that are interesting are you looking for, or what would be interesting to discover?
Say that again. I missed the beginning and then I didn't.
What other kinds of astronomical objects are you looking for, or?
What other kinds of astronomical objects we are looking for in association with LIGO events?
Yeah.
Okay, so in association with, okay, so we expect to have 4 types of astrophysical sources that LIGO can see. 3 we talked about already, which is binary black hole, binary neutron star, mixed neutron star black holes. We are looking primarily for those. Another possible source would be a nearby supernova, which is unlikely to happen, but it could. And if that would happen, LIGO would be able to see it as well, and we would follow it up as well. Although, to be honest, if a supernova would happen at a distance that LIGO can see, you probably don't need DCAM to see it. You know, so yeah, you can step outside and look up, basically, because it will be very close and it will be, yeah. But certainly we are, if there is a signal that comes with type unknown, right, and a region of the sky that we can reach, we are probably going to look for it because there is a potential of discovering a new type of source that we haven't heard before. That's the other thing. We know that we know of these 4 type of things that LIGO could see because these are astrophysical objects that we know of, and we know that they have the right mass, the right density, and they are in the right configuration to generate quadrupole emission. But if there's something else out there we haven't seen yet, and in the world, in the history of astronomy, surprises are often happen sometimes. If something like that happens, we probably will look at it as well. What strategy we will use, I don't know. We will scramble to do something, but because we haven't exercised that yet.
So we take a last question. In front of you.
Okay. Pode. I think there was a question behind you, right? No? Okay.
May I ask a question?
Okay, you can ask and she asks, and then we are done. Okay.
Okay. My question is, can we study physics beyond standard model with neutron stars colliding?
That's a very good question, and way beyond. We should have finished before the last question, because I think I will pass on that one because I know that people are coming up with interesting ideas for the story of the black hole mergers, and those are the ones I've been paying attention to because I'm looking to see if there are some signatures that could motivate an observational program. On the neutron star merger side, what I'm seeing so far are attempts to interpret and complete the picture from the point of view of astrophysics, and some things as well related to the formation of the heavy elements. But that's not beyond the standard model physics, but actually it's pretty much a lot of nuclear physics and things like that to understand the actual opacities and formation of those elements. So at the fundamental level, I understand that, for example, okay, comparing the time of arrival of the gravitational waves and electromagnetic waves and trying to infer limits on the speed of propagation of gravitons. That's one of them. But other than that, I'm not super familiar with other other studies that are going on the fundamental physics side. Maybe somebody else in the audience is an expert. Okay, you'll hear more about it in the afternoon, I guess.
No, I mean, the point is if you can accelerate standard model particles up to pretend that it's a collider. So there's been proposals to use stuff falling onto the central supermassive black hole as using that energy to produce something else. But I guess that the game in a neutron star is that it's so much far away and there's so many things that you don't know that you couldn't also, I mean, even if you were lucky enough to observe something, you couldn't distinguish it. Already in producing gamma rays from the acceleration of normal material. One thing that is very well known that it's unknown and that you can study very well is you don't know the equation of state of the nuclear matter in a neutron star. But it's not beyond the standard model, but it's something very unknown at the fundamental level, and that's studied, but it's not beyond the standard model.
Will the DA camera continue to observing these events after the DS observations finish this year?
Yeah, so the context for the question is that the Dark Energy Survey is planned to finish its nominal observations later this year in December, and the question is about the future of this observational program. So yes, the camera will continue to be available to the community for a decade or more, or as long as it lasts. And our plan is to continue to pursue a dedicated observational program for this particular science. And there's been a lot of support from the CTIO and from all the relevant parties in order to do that.
Okay, so if you allow me, before we go to the poster session, I would like to make a comment. Because of the students, I think it's good to know that. I mean, right now we've seen a lot of these fantastic results, very interesting, very exciting. And that Marcelle is showing, at the very beginning she was working in many topics that people may think are boring, like making the dark energy camera working in the hardware, working in codes and so on. So it's just, I think it's good for the students that we have to do work that's extremely relevant, but may seem a bit boring. And it requires, work, it requires ideas, it requires, all our intellect to make these things work. And that's part of our career, and we do it every day, So we see like the tip of the iceberg of all the work that's involved. But it's very important for us to know that, sometimes you're working on something and say, well, but this is, I want to discover the dark matter. Yeah, but to discover dark matter, you have to do all these models and these calculations and work on the experiments, and as we said before, work on all the possible backgrounds and contaminations, and study the systematics and so on. So we always say that it's easy to measure something. The hard part is to establish the error bars and the systematics, right? So that's all that it takes to get a very good result. So just that comment. I don't know if you want to comment on that, but. And of course, she's builder of the Dark Energy Survey because of the work that was involved since the very beginning. Okay, so now we go to the poster session, but also I would like to say that we were lucky enough that we changed the schedule a bit. So as this talk was a little bit off topic, it was like the closing of the first week of the school. But since the talk is now, we will have Marcelle probably to ask questions in the afternoon too. So if you have more questions, we'll have questions from her. And now, yes, we are ready for the poster madness. And I would like to ask Iago to talk about his poster. Oh, yes, and let's thank again the speaker. Thank you. Thanks.
So hello everybody. This is my work. It's constraints on neutrino decay scenarios with electron antineutrinos disappearance experiments. In this work, I assume that neutrino decays according to a very specific model that's called Myron model. That's called Myron model. Myron is a scalar particle. Here we consider massless, and actually, the model says that a heavier neutrino decays in a lighter neutrino, and in this Myron, of course, when you introduce a new coupling, you have new coupling constants, and we need to find the bounds on these constants.